Welcome you all to this Cryo-EM course, and now we are going to discuss more about 3D reconstruction and the image processing. So in this couple of classes I am not going to talk too much details about the theory behind that image processing and 3D reconstruction, but I will just give you a overall idea how to do or perform that 3D reconstruction and determine the 3D structure. So generally we are organizing many workshop, and also I have a plan to arrange another course where we are going to discuss more about the 3D reconstruction and the principle behind that each and every component. So I already told that for 3D image processing what is required. For the 3D image processing, most important part is that first we need the raw data. Raw data means whatever 2D images we are collecting in the microscope, that we have, and then next one we have to consider, or we have to take those raw data for the image processing, and those raw data most of the time we call that micrograph. Last class I already showed that how this micrograph looks like. But also here you have to remember one important part, that whenever we have micrographs we have to do the motion correction. That is one of the important part, and that also help us to improve the signal to noise ratio or power spectrum that we already discussed, but today we will just go through that little bit more, and it will help you to understand that how we are doing motion correction. So initially if you look at my slide, you can see that initially we are going to focus on some images, normal images. Even if we are in a football match or cricket match and everything is in motion, sometime we want to take an image. So if we are taking an image and if it is in motion, so internally our camera, or if it is our phone camera or any other camera, there is some kind of processing it is happening, and it is giving us an integrated image of that particular object what is moving. So that help us to see those object properly. So if you see in my slide, so look at my slide here, you can see it. So the first image, if you pay attention to this particular first image, so you cannot see anything, it is looking very blurred. But if you gradually go so you can see there is some object is there which is trying to find something, and it is looking like some kind of garbage because image is not very clear. But if you slowly go in a third image or fourth image and fifth image, then you can see that basically this is a nest and this is a bird, and it is trying to go inside that nest. So here there is a motion because constantly these things are changing when we collected that image, and that change you can see it here gradually. But if you just align those frames one by one with each other, and then you can make an integrated image, so you will get this kind of image. So when something is in motion and you try to take an integrated image, your image will be blurred, so lot of fine details you will lose it. So here you can see, this is from this one also you can tell this is a bird and this is a nest, but it is very blurred image. But if you have all the fine details, if you want to see that feather color, what eye, and all the details about the nest, you have to realign those frames, and then you have to get an integrated image. That is basically called the motion correction, and that we already discussed couple of times that how it is happening. Here also again a similar kind of image again. So here this is a blurred image of this bird, so there is a motion, but that when we integrated all these images, we can find out a very high resolution details about this bird. So exactly same mechanism we are implementing when we are doing our cryo imaging. That is, I already mentioned couple of times, if you just recall your images, that whenever we collected data, we are collecting a multiple frames. So something like that, generally what we are using 40 to 80 electron per angstrom square. total electron dose, and when you have the electron dose, generally per frame we are giving exposure 0.4 seconds. So, total time for the exposure, total time for the exposure, if we just exposure time, if we just consider that 8 second, and then per frame exposure, it is per frame exposure is this one, 0.4 second. So, if you just consider that total exposure is 8 second and per frame exposure is 0.4 seconds, what is happening? So, you can consider that 8 divided by 0.4, so you will get total 20 frames. So, whenever we are collecting an image, we are not collecting an integrated image, we are collecting multiple frames, and here if you just use 8 second exposure, total exposure time, and 0.4 seconds exposure time for individual frame, you will get total 20 frames. So, here you have the 20 frames you are going to collect, right. So, total 20 frames it will come, and now if you just consider that, okay, this is my frame number 1, this is my frame number 2, this is my frame number 3, this is 4, 5, what we have to do, you have to align this frame with each other, and if there is a motion because of this thermal drift, when the electron beam is passing through the sample, there will be lot of energy transferred to that amorphous ice, and there will be a thermal drift. Because of this thermal drift, if you just collect an integrated image of the 8 second, then you will get a blurred image, what I showed previously for that bird, or bird is going inside the nest. But if you just collect only 0.4 seconds or only 0.2 seconds, then that due to thermal drift, that motion will be less, and it will help you to correct when you will just calculate the cross correlation between frame number 1 and frame number 2, or frame number 2 between frame number 3, and again frame number 3 between frame number 4. You can correct those drift and you can align them together, and you will get an one integrated image where your contrast from this, after alignment you are getting an one integrated image that is basically give you the good contrast, good signal to noise ratio of that particular image, and that is called the motion correction. So, here what is the motion correction? So, motion correction is the process of using some algorithm to correcting for the motion of the electron microscope stage and the sample ice itself to recover image quality lost by the motion blurring. So, due to this motion, thermal drift or the stage related problem, due to this motion we are losing high frequency signal, and we are correcting those things using that motion correction. Though this is our the first step. So, here you can see when I was talking about that, we can correct 20 frames, and if we just consider one individual frame, you have very low intensity and low signal is recorded. So, if you just go any individual frame, that frame number 1 or 2 or 3 or 4, you will get a very low contrast images, and that you can see that single frame very low contrast images is here, where we have some kind of object in this particular location, but we are not very sure what it is. So, here also you can see, because overall electron dose is very low in one particular frame, because total electron dose is 40 to 80 electrons. Now, if you have a 20 frames, if you divide that total electron, that you have a 40 electrons and for 20 frames. So, per frame you have only 2 electrons. That is the reason your individual frames are not that good contrast, but when you align all the frames, and then you can see this is looking very crispy images. So, now here you can see this is without motion correction and with motion correction. So, same image without, when we align all the frames, you can see the same location, you can see all this object, and the contrast is also very good. Now, if you pay attention, without motion correction your images will be blurred. Same particle you can see it after with motion correction, and lot of fine details you can see it, where you can see, pay attention to those places where the boundaries are very much clear, but here the boundaries are not that clear. Here boundaries are not that clear. So that tells you that motion correction is important to improve the fine details. If you don't do the motion correction, your fine details will not improve. So here I took this video from the CryoSpark guide. That is a very nice representation. So when you have sample in the eyes, those are the individual protein molecules you can consider. That everything you can see, there is a movement here. So in this particular case, you can see that all the proteins here, all these proteins, there is a motion. So if you try to make an integrated image of all the individual frames, what you can see, the same particle here or same particle here, it has position some point here, some point here, and some point here, and you will get an integrated blurred image if we don't do the motion correction. The next step, what we are doing, we are corrected individual frame motion, and if you look at that, there is a motion of those particles, but the position is exactly same. There is not too much change in the position. That will not erase, or it will not filter your high frequency signal. So that is the most important part here. So one thing we all have to remember, that whenever we are doing those tasks, that okay, so we are always looking for a high frequency signal, and that high frequency signal should not deleted from our images. So here I just want to show you one thing. If you just recall your previous our previous discussion, when we have a sample, before the sample we have a parallel electron beam, and then all this parallel electron beam, it will go through this particular point, and then they will come here, converge in particular plane, and it will give us an image here. So basically this is the parallel electron beam. So parallel electron beam, short form I am writing that. Then we have the sample here, and then when the electron beam is coming, this is the point where we are getting all the diffraction, that is called the back focal plane. So if you just consider this is the back focal plane, and from where first electron beam is converged. So if you just go to the opposite, where all these things are coming from, that is called the front focal plane. So if things are in the front focal plane, if the electron beams are converged in one particular point, we will say that this is a front focal plane. So front focal plane is above the sample. So you can say that front focal plane, and front focal plane will be above the sample, and back focal plane will be below the sample. Now here we are getting that images. Now you have to remember one thing, that okay, so when all these signals are transferred, so when these signals are transferred, that is called the contrast transfer function. So we are not going in details about this contrast transfer function and how we can calculate. Only thing you remember, that signals are transferred, and all these signals merge together and give us a complicated function like that. So this is amplitude, and this is frequency or spatial frequency, whatever we can call. So you can mark it that spatial frequency, this is amplitude. So this will be +1 and this will be -1. So in this particular region at beginning, this is called the low frequency signal. And when the signal is going there, that is called the high frequency signal. Okay. So if we just remember our diffraction pattern, previously we discussed these things, that when we have the diffraction pattern at the central part, we are getting a very dense white patch, right. So if you look at remember the power spectrum, and then we are putting those dots, right. So when we have that signal that okay, there is a sine wave, it is going like that, right. when sine wave it is going, and we want to plot it, this one in diffraction pattern, we'll plot it that okay, the k equals to, this is frequency and this is the amplitude square we are plotting. So based on that, so if the position of this wave is different, then this vector position it will change. So we are getting dots, right? At the center you will get a very white spot, and then there will be two dots in two different position. So here also that you will get that dot. So at the center you will get a very white bright spot, and then you will get that dots. So when there is a frequency is more, so if you just consider, okay, this is the frequency, if we just consider k equals to 3. So if we want to plot that one, what we are going to do, we are plotting frequency k here. So this is our plot of the diffraction, and diffraction spot it will come k equals to 3. If you recall all the previous diffraction pattern when we discussed this thing. So you can also recall that okay, at the center you will get the amplitude contrast and all the bright light it will come, and then high frequency signal you will get it in the far away from this center. So those are called the high frequency signal. Now if we want to plot this one, this is called the low frequency signal, and then your high frequency signal. So wherever the spots are going very far, those are high frequency signal, and this is will be low frequency signal for your images. So now this is basically when we, if you just recall your previous one, this diagram you can see that okay, I am telling that okay, this is a low frequency signal and this is the high frequency signal. So when the signals is converted, when we are collecting those images in after the motion correction, what we are going to collect. So most of the times when I told you that if you look at your slide that when bird is trying to enter, even third image you can see a bird and a nest. So that is basically low frequency signal. This low frequency signal you can see overall architecture of the nest and the bird, but you cannot see high frequency signal because you cannot see the eye very clearly, you cannot see the difference between the wing. So what is happening when, if you don't do the motion correction, you have low frequency signal, and then suddenly you are losing all the signals like that. So if you don't do motion correction, you have the low frequency signal. So that is help you to align preliminary and see the overall architecture, but you cannot see the fine details because fine details is mostly coming from the high frequency signal. Now when you did the motion correction, you have a low frequency signal and also you restores your high frequency signal also. This is your high frequency signal and this is your low frequency signal. So after motion correction you restored here you can see you didn't do the motion correction. So this is without motion correction and you lost mostly high frequency signal, but here you did motion correction and you recovered all the high frequency signal, and that is the reason you can see all the details, even eye color, that different pattern of the wing. So same thing for the biological sample also. When we want to do a three-dimensional reconstruction, we want to recover all this high frequency signal. If we don't do the high frequency signal, it will be very difficult to get all the side chains or helix and the hydrogen bond formation, and that is the reason we are doing all of this task. Now always remember at the beginning what I was telling, that low frequency signal means overall architecture you are getting. So if you just consider, okay, this is a duck, I draw this one most of the time. So this is a duck. Now this duck, if you just see that overall architecture, it is something like that. So anyone can see and tell that this is looking like a bird or duck something, but you cannot see all the details if the high frequency signals are gone, right? So if there is outer line, if there is this kind of line, you cannot see those details. but overall dark you can see it at low frequency signal. So this information will use it for 2D classification, because you remember first we collected the data, the next one we did the motion correction, then third one we are going for classify our data. So when we have an image, in that image we have a protein sample. If you just consider that this is my protein sample, so sometime this protein will be overlapped. So you already saw my data multiple times, I showed you. Now what we have to do, we have to just individually go and pick those particles. So here we'll pick those individual particles from here, and then we'll segregate into different classes based on their morphology and how similar they are. So if this is coming from image 1, so if we consider this is our image 1, then I have another image, the second image also in same way, that I have some particles here, that I'll just use this one, that okay. So again there is some particles like that, and then what I'll do, again this individual particles I have to block, and I have to pull those individual particles from here, and then I have to make this particle stack where from this is my second image. So image 1 I'll get some particle stack like that. So maybe I have 100 image, this single particle image, and then image 2 also I'll get single particle image like that. So this will come from particle, you can say this particle underscore 01, that one stack file, right. So image, and then you can say this is only the particle 02, that image, right. So you are getting individual particle stack here. So this individual particle stack we have to stitch them together. So if you just consider this particle stack has 100 images, this particle stack has 95 images, then if there is a image 3, you just consider this is the image 3, and we pull out particle like that, and now I have 120 particles. Okay, so now from this 3 image, how many particles we are getting total? So if you just add all of them together, we will get the total number. So we will get that 315 particles. So 100, 120 means 220 plus another 100, 200, 320 minus 5. So we are getting total 315 particles. So this 315 particles, it is called the stack file, where we have all the particles together from this 3 image. So now if you have 1000 image and every image has 100 particle, you can imagine how many particles you are getting. So that is called the stack file. That stack file we are going to use it for 2D classification. What is that 2D classification? Let's take a look the 2D classification. So if you come here, so our next target is that cryo-EM image processing and single particle cryo-EM image processing, and that is our first aim to classify our data set into 2D. What is that 2D? So this is our first step. So already image collection is done, motion correction is done, then CTF correction will be done. We are not talking too much about that, but definitely after motion correction we have to do the CTF correction, that is basically signal transfer, that contrast transfer function. When the CTF will be done, then CTF, when you will do the CTF, will calculate only 2 parameters, defocus value and CS value. When we have that one, we are going to the next step, that is our 2D classification. So basically 2D classification is the most important part for this workflow, and this is one of the first step where we are, this data set is grouping together with the particle of the similar view to enhance the signal to noise ratio. Okay, and this also meanwhile discard the invalid particles or contaminants. The class averages can be used for assessing the degree of the heterogeneity in the data, whereas the good one are chosen for the calculating the initial model. As particle images of similar orientation, the particle images of similar orientation are related to each other by the image translation and rotation, and clustering like particles that will give us the 2D classification or 2D averages. So, what we are doing, similar kind of images, we are grouping them together and then we are building a same kind of particle and averaging. When we are calculating the averaging, what we are averaging? We are averaging the signal, we are averaging the contrast, mainly the amplitude, and rest of the noise we are removing. That is why we are telling we are increasing or enhancing the signal to noise ratio. And when we are aligning, that is very important term, that we have to align our data, align our particle. So, we have to rotate our particle, and then we have to, if required, we have to calculate the x and y translation as well as the rotation, and then we can align the particle. In all the cases, we will apply the cross correlation values also. We will calculate the cross correlation value and try to align those particles, and cross correlation value will be calculated based on their signal. So, that is basically called 2D classification. So, if you come here, I will just give a very simple example, that okay, you have a two different architecture, one is the triangle, one is the square. So, but it has a different movement, so they are not center all the time. This one is in center, but they has a different position. So, all the cases, if I want to align like that, what we have to do, this particle I have to rotate it little bit in this direction, and I have to make this same thing also. This particular particle I have to rotate in a certain angle, and here this one is shifted. If I have to bring it to the center, I have to make a move and make a move in this direction. Same thing also, that x and y translation is required to bring this particle into the center, and then a rotation is required. Same thing also here, we have to move this particle and make it in the center, and then there will be some rotation. So, what we are calculating, we are aligning the particle and then classifying them into two different group. So, there is a two group, group 1 and group 2, and also then we are calculating the average based on their signal. Signal means how much signal to noise ratio is there, and then for that we always have to do some kind of rotation and translation also, that x and y translation and the rotation at different angle to align them together. So, align, so here this 1, 2, 3, 4 and 5, it will be in same group, but we have to do this rotation, translation, and then we have to align them together and get this class. So, at this moment I will stop it here, and next class we will discuss more about this 2D classification and the 3D classification, and they are all are interconnected, and I will give you some actual example that will help you to understand this entire pathway. Thank you all for your attention.